Imagine an explosion so powerful it could outshine an entire galaxy filled with 100 billion stars. This isn't science fiction, it's a daily reality in our universe. These titanic events are called gamma-ray bursts, or GRBs for short. For a few fleeting moments they become the brightest objects in the entire cosmos, unleashing a torrent of energy that staggers the imagination. They are the universe's ultimate flashbulbs going off in the distant dark corners of space. These bursts aren't made of the gentle visible light our eyes can see, but of gamma rays, the most energetic form of light. This light has so much punch it can travel across billions of light years to tell us a story of cosmic violence and creation. As we gathered more data on these enigmatic flashes, a pattern began to emerge from the chaos. Scientists noticed that the bursts seemed to fall into two distinct categories based on how long they lasted. It was like sorting fireworks into sparklers and cherry bombs. The first type, which we creatively call long-duration bursts, can last for more than 2 seconds, sometimes continuing for several minutes. The second type, the short-duration bursts, are much quicker, vanishing in less than 2 seconds, sometimes in just a few milliseconds. This simple difference in timing turned out to be a crucial clue, pointing toward two completely different origins for these cosmic detonations, each one a story of spectacular and violent celestial death. The long-duration bursts are the dramatic swan songs of the universe's most massive stars. We're talking about stars that are dozens of times more massive than our own sun, true giants of the cosmos. When such a star exhausts its nuclear fuel, it can no longer support its own immense weight against the crush of gravity. Its core collapses catastrophically, imploding in on itself to form a brand new black hole. As the surrounding material from the star falls toward this new black hole, a complex and powerful engine is formed, launching twin jets of superheated matter away from the star at nearly the speed of light. If one of these hyper-focused jets happens to be aimed directly at Earth, we see it as a long, brilliant gamma-ray burst. Short-duration bursts, on the other hand, originate from a different kind of cosmic catastrophe, a merger of two incredibly dense, dead stars. Detecting these powerful but fleeting events is a monumental challenge. You can't just point a regular telescope at the sky and hope to see one, because Earth's atmosphere thankfully absorbs these high-energy gamma rays, protecting us from their harmful effects. And this means we have to go above the atmosphere to hunt for them. We rely on a network of sophisticated space-based observatory satellites that are specially designed to act as our eyes in the gamma-ray sky. Telescopes, like NASA's Swift Gamma-Ray Burst Explorer and the Fermi Gamma-Ray Space Telescope, are constantly scanning the heavens, waiting for that telltale flash of high-energy light that announces a new burst has occurred somewhere in the distant universe. When a satellite like Swift detects a burst, it's a race against the clock. The telescope can autonomously and rapidly pivot itself to pinpoint the burst's location in the sky within seconds. This information is then instantly relayed down to Earth and broadcast to a worldwide network of astronomers and other telescopes. This rapid alert system is crucial because the gamma rays themselves are just the beginning of the story. The real treasure trove of information often comes from what follows: the afterglow. This is the fading light from the explosion's fireball as it slams into the surrounding gas and dust in space, causing it to glow in less energetic forms of light. X-rays, visible, light radio waves. Section 4. Cosmic laboratories and distant beacons. So why do we care so much about these distant, violent explosions? The answer is that gamma-ray bursts are far more than just cosmic fireworks. They are invaluable scientific tools. They serve as unique laboratories for testing the laws of physics, density, temperature, gravity. By studying the light from these bursts, we can test Albert Einstein's theories of relativity and probe the fundamental nature of matter and energy. They push our understanding of physics to its very breaking point. Furthermore, because these bursts are so incredibly bright, they act as powerful beacons that illuminate the very distant, and therefore very early, universe. Some of the gamma-ray bursts we detect come from a time when the universe was just a fraction of its current age. The light from these events has traveled for over 10 billion years to reach us. That light carries with it the fingerprints of the gas and galaxies it passed through. By analyzing it, astronomers can study the composition of the first galaxies and probe the era when the very first stars were igniting and lighting up the cosmos. They offer us a direct glimpse into the universe's formative years. The study of gamma-ray bursts is also inextricably linked to our understanding of black holes. Collapse of a massive star merger of two neutron stars, both end with the formation of a black hole. Section 5. A safe distance from the fire. Naturally, when you hear about an explosion that can outshine a galaxy, a question might pop into your head. Could one of these happen nearby? What would it do to us? It's a valid concern. If a gamma-ray burst were to occur within our own Milky Way galaxy, and its jet were pointed directly at Earth, the consequences would be catastrophic. The intense flood of gamma rays and other high-energy radiation could severely damage or destroy our planet's protective ozone layer. This would expose the surface to harmful ultraviolet radiation from the sun, potentially triggering a mass extinction event. It is a sobering thought, a reminder that the universe can be a dangerous neighborhood. However, my Dramain son, and this is very important, you can sleep soundly at night. The chances of Earth being harmed by a gamma-ray burst are extraordinarily low. First, the types of events that produce these powerful bursts are themselves quite rare. Truly massive stars that lead to long-duration bursts are few and far between, and most of those stars don't produce a GRB when they die. Similarly, pairs of neutron stars and those that are close enough to merge are not common. The universe is vast. These violent events are the exception, not the rule. Second, for a burst to affect us, its narrow jet of energy would have to be aimed with pinpoint accuracy at our tiny planet. Most gamma-ray bursts fire their jets out into empty space, missing everything.